they want, if it be petabytes or terabytes, and know that it's going to show up. Know that the bandwidth they need at the time that they need it, for the duration they need it, will be available, and that there's hope that their application will be able to run. And the final point is simply to simplify everything for the physicists and the network operations folks along the way. So that's the hope. The design criteria for Brew was from the perspective of the people who were not network engineers. If you listen to the plenary talk that was done earlier, one of the most important things I heard Ed say several times is that he's not a network engineer and he doesn't want to know a lot about all the pieces and components along the way, other than to know that he can ask for bandwidth and get it and it'll work. And so that's sort of the notion of looking at this. And the Brew functionality is really divided. There's two components. There's what we call the front end, which is what the end user sees. And it worries about who you are, what it is you're asking for, what permissions you have, and scheduling the request for bandwidth. The back-end portion of Brew is something that needs to be trusted and known by the network operations folks, because the back-end is actually responsible for setting up the tunnel. And in the case of the Abilene backbone, it's the MPLS tunnel. And so it needs to be somewhere where the network operations folks trust it and can interrogate it and rely on it. Plus, the back end, there may be several back ends. The back end I'll talk to you about that we've done is capable of setting up MPLS tunnels on Juniper routers. Trivia question, do you know why we chose Juniper routers? That's what's on the Abilene backbone today. But we also have folks that are doing backends. Some of our friends at ESNet with the Department of Energy taken the Brew front end and they've done a back end for Cisco routers. We have some folks that are looking at this in the Dragon project that are going to do a back end for some high-end Ethernet switches. Using SNMP to set up the paths and such. So that's the whole notion behind this, is having a front end that is usable by the user, and then a back end or several back ends that may be specific to the network hardware and the topology that follows. Does it make sense? You all thinking about taking a nap, or is it just me? Okay. We've talked about this. The thing that I didn't talk about, and I'll try to show you, is the user authentication. We thought about this a while because we wanted to be able to, let's say that I'm at Caltech, the university, and so I go ahead and identify myself as a physicist there, and I want this path from Caltech to CERN. Turns out that the path that I need to take will go up through Canada, will come down, will go through the UK, will go through a couple of other places. Somewhere along the way, I either need to send email to my friends who will send email. That's currently the notification process today. Or if I had some credentials that I could present to them and they could say, well, this is this sort of individual from this sort of institution. He's obviously authenticated. We trust this person, and here are the capabilities that we permit them to do. I was looking for a mechanism that would allow us to do that. As Ted pointed out, I'm with Internet 2, so I thought I could use Shibboleth as the front end, as the authentication mechanism for the front end. And then if perhaps that the other administrative domains, the networking operations center, would run would be a Shibboleth domain, a target, then I could pass my Shibboleth credentials to them, and they would know what to do with them. And it would be, Shibboleth is sort of ambivalent. If Caltech happens to use public key infrastructure to authenticate, but some other university might use Kerberos or something like that. It doesn't matter. It's your responsibility in your domain to plug your authentication mechanism into Shibboleth. Shibboleth will give you some credentials that are useful in other domains. And so, anyhow, that's how we ended up with this. And I thought if I could sneak down and find the actual web page. You can guess what the password is. And hopefully, and this is what the user sees. You're able to get up and remember again the purpose of Brew. Our initial purpose of Brew was to set up bandwidth reservation between two endpoints on a packet switch network. So there are a couple of things you'll need to know as an end user. You need to know the origin and the destination, the IP address. You can put that in, and then you specify the bandwidth. You notice that it says megabits per second. That may be less interesting for you, you greedy gigabit per second people, but you can put lots of zeros behind it for now. And then, so you specify what the endpoints are. You specify the start time, when you'd like this bandwidth allocated, and then the duration, how many hours that you'd like to have it for. A description would be nice if you wanted to enter one, and then you simply ask it to reserve the resource. There are a couple of things that happen here. If you have the sort of credentials that allow you to reserve bandwidth between those two endpoints, if the bandwidth is available, if it's Tuesday and the sun is shining, you know, if you have all the necessary credentials to do that and the bandwidth is available in the path, you'll get back a page that tells you that your bandwidth has been reserved. If for some reason it fails, you'll get back information telling you why it failed, and it might give you an email address if somebody it could give you an email address. It won't give you my email address, but it might give you an email address that goes to the Abilene NOC or goes up to Canary, or because it lets the end user know who they could talk to if the request fails. So you can make the reservation, and it'll tell you that it's either made or not. If it tells you it's made, as an end user, you're done. There's nothing else for you to do. Other things you can do is you can go view reservations and see what the status of the reservations are. And depending on what type of user you are, how much you're loved, you may be able to see your own reservations. You may be able to see other reservations. If you're competing for bandwidth, because one of the greedy gigabit people have reserved all of it, you at least might know who to talk to about that as well. You can find out some things about yourself, and you can log out. One of the things about the Shibboleth is the thing I didn't show you is a very first web page. There's a place where you can register for an ID for Brew across Abilene. And that is the only process that involves some human interaction. When you register for an ID that will allow you to reserve bandwidth, email goes somewhere, and a human being makes a decision whether or not, what to do with that. I'm not sure that's a good idea, but it seemed like a bad idea to let any freshman on any campus start reserving bandwidth across the backbone without knowing who or why. The good news is once you're given an ID with certain characteristics and capabilities, you're allowed to live within those capabilities for however long that you exist. So there really isn't much to it. I mean, if you take the 50,000-foot flyover, you make a request to reserve bandwidth, and the policy engine, it sort of checks who you are, what you want to do, whether or not the bandwidth is available, etc. If the endpoints actually exist, you know, all the sort of stuff The goal at the front end is to try to tell the user whether if there's no hope that this request is going to work, is to tell them that as soon as possible for whatever reason. And it essentially, if it approves a reservation, it puts it in a reservation database, and it just sits there. The reservation management system, which is what we call the back end, doesn't do much very interesting. It runs a cron job. Currently, it runs it every 30 minutes or so. Do you know why we picked every 30 minutes or so? Because for our initial deployment, we were going to let you reserve bandwidth on the hour for at least an hour. Can you do it for less than that at different times? Sure. But for our initial implementation, the project lead decided to do things simply to work through the issues of cross-domain administrative management. So how does Brew work? Well, here's how it works on Abilene. User gets on the endpoint somewhere, says, here, I'd like to reserve bandwidth from these two endpoints. We take advantage of one of the machines that we pretend doesn't exist on the Abilene backbone, like your networks. At our network nodes, we have PCs that are there to help us do other things. One of the machines actually figures out what the ingress edge node router is to Abilene, and using that edge node figures out what the egress point is. The reason we need to know this is because to set up the MPLS tunnel, you need to know, if you know the ingress router on these Juniper routers, if you can find the ingress router and tell it what you want to do, number one, you set up the policy at the entry for the origin. The other is it'll go ahead and do all the neat work that you need to do to set up the MPLS tunnel across the other Juniper routers across the backbone. So from a developer's point of view, that was handy because I only need to talk to one router, which will talk to the rest of the routers. Why am I interested in finding the egress point? Because I may want to set up a bidirectional bandwidth reservation. Still trying to figure out if a user sits down and says, I'd like to allocate 8 gigabits from here to here. Does that mean he's going to have 8 gigabits going from here to here, or from here to here, or maybe he wants to go both ways? And for our initial implementation, because the project director decided that he would do it bidirectionally, so that if a user asks for 8 gigabits, he'll get 8 gigabits going both ways. Does that make sense? Not for all cases, you're aware of that. But if one thinks about doing large collaborative interactive sort of sessions, generally you want to have it flowing both ways. And I'm an old video guy, so I always think about that first. The back end, here's how Brew works. The back end just configures the edge router. When the cron job looks at it and says, oh, there's something that needs to be set up here, it goes out and it communicates with the necessary Juniper routers. It actually uses the JunoS script, and there's actually capability. It's not quite done yet, but it will be out in the third quarter of this year that allows you to use using XML to go ahead and communicate this information to the Juniper routers, so you can sort of set up these almost class of service sort of things in XML script and forward it. There's still some work to be done on the Brew. One is sort of the last mile. The good news is we know how to do this and make it automatically set up MPLS tunnels across Abilene. What's interesting is our end user at Caltech doesn't have, his machine is not directly connected to Abilene. It goes through Caltech networking system, and then it goes through probably Scenic, and then ends up connected. So what do we do about the last mile? Again, the notion of having a Brew or a Brew-like server, or somebody that will talk to Brew in each administrative domain that's willing to go ahead and reserve bandwidth from that point to the next point is useful. And you've already figured this out. If you set up bandwidth reservations, I mean, you have to talk to somebody at the local network and then at the sort of gigapop or the aggregation of network. So we're thinking about that. Other things we're thinking about is what happens if you go from Brew, a packet switch network, to, can I say virtual circuits? You have to apologize. The Lambda rails and all that, I think they're wonderful things, and they remind me a lot of ATM networks. So I've been at this so long, I think of a Lambda as my dedicated wave as a virtual circuit, or maybe not quite so virtual, but it's mine, you know. So we're thinking about what to do here. We're doing some work in the Manhattan Landing in New York City. Happens to be a place where there is a UCLP server, which is what Canary uses to reserve waves, lambdas, going across CANet4. So we're working with them, figuring out how to make the transition from a packet switch administrative domain to a lambda domain, because when you reserve bandwidth, again, as Ed pointed out, the physicist wants 8 gigabits from here to there. He doesn't care if it's going across the packet switch network or if he has his own wave, or hopefully it's not going across an ATM network. But if it is, he doesn't care. And so that's more work to being done. We're also working with folks in the Department of Energy in the United States. They're using the Brew code in the front end to set up to build MPLS tunnels across Cisco routers, across the ESNet. We're working with some other folks as well to figure out how to do this transition. If you want to know more about this, you can email me. You saw how carefully I hid the website where all the Brew stuff is at. You're welcome to go there and look, and one of the things that I've had Sue Young do as we've gone along is if you go to DISCVENUE, it's the second thing up there if you pull down the slides. If you go to that URL, the first page you'll get will be one that'll take you to the sample I showed you, the user page. There's also a blog. All of the development work, decisions made, issues to be considered are all up there. Feel free to go look at them, comment on them, correct them. So I guess I'm done. Yes?
Maybe I missed that. Sorry.
Again, because this is being webcast, we have to make sure that microphones are all the speakers right behind you.
Is it on? Yes. Okay. Maybe I missed that, but do you plan to extend the Brew part from MPLS-based networks to GMPLS-based networks? Do you plan that, or are you doing that?
Yes and yes. I'm working with Tom Lehman and Jerry Sobieski on the Dragon project, where they're using I think it's the Movaz Ethernet switches, where they use them to set up a VLAN, essentially a very wide area VLAN, and they use those switches use GMPLS signaling. So the answer is yes, and the back ends, each back end will address a specific implementation required by the hardware. So yes and yes.
You mentioned the fact that you use bidirectional MPLS LSPs. With MPLS, the LSP is unidirectional by nature. So do you set up 2 LSPs?
Yes.
Or do you use the bidirectional functionality of GMPLS?
With the current software in our Juniper routers, we set up 2 MPLS tunnels. That's why it's important for us to find the ingress and the egress point, is we need to find those routers.
Okay.
And
okay. I was wondering because you could also use the GMPLS extensions to build directly a bidirectional LSP.
Right.
That's awesome.
Right. We're hoping there are several changes that Juniper has indicated will be available in their production code.
Okay.
Being real careful with the words I use here. And since Abilene is a production, sort of a production network for the universities at Internet 2, I'm trying very hard not to break it while I'm doing this.
Thank you.
I think that this may be a little bit out of the MPLS and all this topic of and working with middleware. So it's about the trust links you have between the different components. You have mentioned you have made a shibboleth authentication, right? So how are the credentials progressed to the different domains you are going to?
The assumption that we're making is that each domain will be a shibboleth. Trying to think of the right terminology. Will be a shibboleth origin domain, which means that they can have target services within them, and so that they'll be part of some shibboleth federation. And this is one interesting point that I would be interested in pursuing. Currently with shibboleth, some of the schools are using it to share library material, and so they'll have federations of law schools or federations of medical schools. I'm wondering if having a shibboleth federation of network operating domains would be a useful thing.
We are working in something similar in Gen 2, so it's something that I would like even to discuss with you afterwards. Or
Please,
whatever.
please.
Any other questions? Oh, in the back. Anybody in between here and there? She gets her exercise.
You have chosen a web interface for requesting bandwidth. Have you thought about supercomputer jobs which get into a queue and wait for execution? So you don't know when startup time is, and you need something like delegation or user ID and password into the supercomputer job to get the reservation. And the second question, it's a little bit related. You said that you have your request in a database. This means that every time you want to set up an MPLS path, you have to check the database that there isn't already a request for this time period.
Let me answer the second question first. The database is the information there can be used to determine whether the reservation request can be honored. The database serves as sort of it's sort of the transition between a reservation and scheduling the reservation. So the information in the database is useful for that administrative domain to determine whether or not. And one of the interesting questions is, I mean, you could say we're only going to allow this much bandwidth across the whole administrative domain, or if you're more want to be more realistic, you'll look at the links along the way and figure out if the bandwidth is available in each link. So the answer to the first question is we did not take into consideration that there may be, that the user of the bandwidth may be supercomputing jobs that will run at unpredictable times. And I'm with what Ed said earlier. They push the button, they want it now. But no, we haven't done anything there. One of our goals with Brew is to eventually move, once we think that we have the pieces sort of stable and glued down, is to move from making a reservation that has to be done every hour for at least an hour to making reservations that could happen in short minutes from now, that, and in that case, perhaps from the scheduled supercomputing work, when it got ready to run, the first thing it could do is maybe there'd be a task that says reserve the bandwidth. But there currently is nothing in there for that at all. And I've used up more than all my time.
Thanks, Bob. Our next presenter is Michael Enrico. Trained as a physicist, went to work into the telecommunications area, and for the last 4 years has been a member of the network engineering and planning team at Dante, and will talk about a European bandwidth on demand service.
Thank you. First thing I need is a glass of water, because normally I dry up on these occasions. So I feel like some of my thunder has been stolen a little bit there by Bob, because a lot of the issues that I was going to talk about here he's already covered. So that saves some time in actual fact. So a brief look at the outline. Essentially I was going to look at the motivation for us developing a bandwidth on demand service under the Géant 2 program. Secondly, give you an outline of what we're thinking about doing, and then just tell you the status and come up with a few conclusions at the end of it. So the motivation, Bob has already covered it really, it's basically these point-to-point services. Various projects over the years have started to come to us as the operator of Géant and NRENS and our colleagues in the US, and have said we want some dedicated layer 2 or below connection, point-to-point connection. The networks in between have had various ways of being able to implement that depending on the technologies. And we've gotten together in this handcrafting manner to try and implement those. And Bob has already covered the issues associated with doing that. Well, my example was this particular one here. So this was an HD TV, high definition TV demo done between an institution in Barcelona and another one in Korea. And as you can see from the diagram there, the end-to-end path, which was essentially an Ethernet-based path, an Ethernet-based service, traversed the university network in Barcelona, a regional network, the Redeiris Spanish national network backbone, the Géant backbone, Canary, Canet 4, and then across to Korea and through a number of networks and local POPs there. So it's essentially the same problem. How do we make the provisioning of such services more automatic and more on demand and more seamless to the user, so they don't take weeks to actually set up? So when the Géant 2 proposal was being put together, and you will hear a number of presentations about various aspects of Géant 2 during the course of this conference, one of the research activities, one of the joint research activities that was thought about was an activity to look at a bandwidth allocation and reservation system, and this is essentially what I'm going to be talking about today. It's called GRA3, not a very sexy name, I know. There has been discussions about trying to give it a more sexy name. The one which we haven't really decided that yet, even at this stage. The one we did come up with was BEER, B-E-E-R, which was something like bandwidth end-to-end reservations. So we may yet live with that one. So anyway, that's the one I want to talk about now. And I will also mention a little bit about the one at the top there, which is Service Activity 3. Which is performance. I can never remember what it actually stands for. It's performance and allocated capacity end to end. You will hear about the PERT aspect of this particular activity later during the conference, but I'm going to mention a little bit more about the premium IP provisioning part of it. So what is JRA3, or perhaps BEER, as it may become? What's it all about? It's about trying to research and develop the notion of a connection-oriented, or layer 1 or layer 2 bandwidth on demand service, which is suitable for the European research and education community. So that's one that can be reachable by as many users within Europe as possible. And some of the issues that we want to look at are essentially to address the multi-domain aspect of the problem, the fact that there are many administrative domains along the path, the fact that they're heterogeneous in nature, so their technologies are very different. How do we make the provisioning more automatic, and how do we introduce the element of advanced reservation? Well, initially, we think, well, from a point of view of pragmatism, many of the networks involved are not going to have what you might call real light path capable infrastructure. So we might have to make use of things like layer 2 tunnels, layer 2 VPN approaches in those domains. And then as the domains involved become light path enabled, then introduce those technologies into the work that JRA3 does. So there's about 260 man-months of effort over the 4 years of Géant 2. Those are the participants taking part. So they're Dante and a number of the European NRENs. The ones highlighted in bold, GAR, GRNet, HEANet and PSNC are the work item leaders. Dante, the overall activity leader, which is myself. And as I already mentioned, this is quite closely related to the service activity number 3 under the Géant programme. And the idea here is that useful results coming out of this will feed into the enhancement activity, which is basically part of service activity 3. Quick look at the work items. The first work item, well, work item 1 there is obviously the management that all of these activities have associated with them, basically my time and the time of a few others. Work item 2 is a requirements gathering and state-of-the-art phase. So this is essentially trying to identify the potential users in Europe, their requirements, and the requirements that their applications place on the network. And then a comprehensive survey of what technologies are out there today that might help us to actually design a service. And GRNet have been leading this activity. I'll tell you shortly what the outcomes of this are. Work item 3 is the service specification phase. So that is basically studying the key issues, architectures of provisioning systems, how do we take into account policy, so whether or not a user making a request is actually allowed to make that request within a given domain. The components that are required, so bandwidth brokers and things like that. What interfaces will exist between these components? Control plane issues, so integrating, for example, with automatic control planes that might exist in a network that come out of the box, so to speak, those that are already there, for example, a GMPLS-enabled network, and then addressing some of the issues to do with monitoring. And essentially then derive a number of specifications for a service in a phased manner to try and break the problem down into manageable chunks. And as you can see, GAR, the Italian research network, people there, Mauro Campanella in particular, is leading that one. 53 man-months of effort. The other 2 work items have yet really to begin. They are the implementation, so that is where software components need to be created, or hopefully in our case adapted from others who are willing to sort of help out. We don't have a huge amount of effort there. But where those components need to be created or adapted, then that implementation work will be done under that work item. That's led by PSNC. And the testing and service validation activity is essentially testing those models and testing the components that get built. And that's being led by HEANet, which is the Irish Research Network. So the status of the work at the moment is that work item 2 has done most of its initial work. So it has produced a deliverable, which is a bandwidth on demand user and application survey. This has been finalised and is being reviewed at the moment. I have to say the response from the various user communities we approached to try and find out what their requirements were a little bit disappointing. I mean, they weren't terribly responsive. Part of this is down to the fact that the process by which we tried to get the information was essentially by sending them a questionnaire. So I think we're going to revisit that particular deliverable within the next year, and I think we're going to have to spend a lot more time basically meeting up with them and talking to them face to face to find out what their real requirements are. And then the second deliverable there mentioned is a state-of-the-art review. This has just recently been completed and is now undergoing its final editing, and then we'll go through the review process. Work item 3. This has started now. Discussions are essentially ongoing about things like the architecture and the framework of any service that we will develop. A face-to-face meeting was held in Zurich in April, and that was when the first real discussions took place. And work has now started on an initial deliverable, which is a high-level specification for what is still essentially a manually provisioned bandwidth on demand service, but one in which streamlining as much possibility to streamline that manual processing, that manual provisioning process has been put into place. Some of this will hopefully become a bit more clear later. With regards to the user and application survey, essentially, as I said, the results were a little bit disappointing. 12 projects were approached, the usual suspects, the grid users, big science users and so on, and we didn't get a great deal of response from them. The questionnaire was looking at things like control issues. How would you expect to be able to control a bandwidth on demand system? Things like reliability. So do you expect to have some options for reliability, for different resilience of the service, whether or not it's restorable? And then other issues as well. Were they interested in taking part in a pilot, maybe a year or two down the line? Essentially, what emerged from that was that there was a need for a bandwidth on demand like service in Europe. It's still essentially a niche service, but nevertheless, some of those user groups sort of spoke up and told us a little bit about what they wanted. A web services approach to making reservations and so on looks to be quite popular. The ability to schedule reservations in advance was definitely important. When we asked them about their bandwidth requirements, we were rather hoping they might say something like, "Oh, well, we're only really interested in a granularity of a gigabit." But in actual fact, they came up with all answers, ranging from 10 to 10 megabits to 10 gigabits. So there was nothing terribly conclusive there, other than they all have very different needs. And we then asked a number of those projects if they're interested in helping us out with a testing phase later on, and some of them were. The state-of-the-art review looked at various technologies, so transport technologies. It looked at the sort of Sonnet SDH type switching boxes that you see around some networks, the use of virtual concatenation and LCAS, GFP encapsulation of Ethernet. Then we looked around to see what bandwidth brokers there were around in the scene. A lot of the bandwidth brokers that were looked at were essentially at the IP layer, and they were projects that had finished a few years ago, so they weren't terribly interesting, some of them. But some of those there, what's going on in the Dragon project, what Nortel are developing with their DRAC and so on, are definitely of interest for future investigation and hopefully some collaboration with. And then we looked at things like the various signaling protocols, and essentially wrote a deliverable which just provides an overview of all of these technologies and how they might be fitted together in our future development work. So one of the first things we faced when discussing this service was, well, what exactly does bandwidth on demand mean? And of course it can mean very many things. So in order to be able to actually start making some progress, we've decided that we're going to focus on an Ethernet service, if you like, an Ethernet private line service. The point here is that that Ethernet private line service should be able to be configured across multiple domains when they're using different technologies. So one domain might be using Ethernet encapsulated in Sonnet SDH, next domain might be using Ethernet encapsulated into layer 2 VPN, and then address the problem of stitching those together. So this is rather like Bob was talking about just now. There are obviously many other definitions for a bandwidth on demand service. You could, for example, consider trying to provide a Sonnet SDH path service, but that really is essentially just for future investigation. The key point is to address the issue of heterogeneous network technologies. And within the architecture, a number of functional blocks have been defined. Now, none of this, by the way, is set in stone yet. This is essentially what I'm trying to do here, is give you an insight into the way that the people who are working on this particular work item have been thinking over the last few weeks. So they've come up with the notion of an interdomain manager, a domain manager, and a technology proxy. The interdomain manager is essentially something that manages calls as they progress from one domain to another, uses some authentication and authorization, and is also responsible for interdomain routing. And then there's a domain-centric manager, which is a little bit more specific to that particular domain and determines intradomain routing, provisioning within that domain, has a reservation scheduler in there, and it also takes care of any monitoring requirements. And then there's this notion of a technology proxy, and this is where, although the domain-centric service manager, the DM, may well deal with provisioning in a more abstract manner, the actual network elements, of course, will be very specific to a particular vendor. So the technology proxy is a function to translate provisioning requests from a more generic form into a vendor or technology-specific form. Where possible, we would like to reuse existing components. There may be an NMS in that particular domain which has got an interface in it that allows service requests across that particular domain, things like UCLP, for example. Some functions may actually exist out of the box. So some networks might have a GMPLS-enabled control plane. So the question is then, how do we interact with that within this framework? And then they've also been thinking about issues such as routing. So, for example, there's been an interesting debate on the email list about a disagreement between two views. So these are called option 1 and option 2 here, about how to do inter-domain routing. And I'll have some diagrams shortly that will hopefully make this a little bit clearer. But in the first option, the first domain encountered by the service provisioning request essentially determines the sequence of domains that need to be traversed. And then the advantage of that is that each domain may implement its own inter-domain routing algorithm, and it also allows for inter-domain traffic engineering. The other option is that each domain simply determines the next domain. Each domain there, the issue there is that each domain must implement a common inter-domain algorithm to avoid loops and so on. But arguably, this is considered to be more scalable than option 1. Like I say, none of this is in stone. This is just an insight into the discussions that have been going on amongst the people working on this. And then there's the issue of intra-domain routing, and that's essentially the goal here is to find a path within the domain between an ingress and egress point that satisfies a particular constraint, such as bandwidth. In the future, there might be other constraints that are taken into place, like delay. But there, each domain may use its own routing and traffic engineering algorithms. And then there's the issue of signaling. So how to set up and tear down these things. And again, there's two options here, two options to be considered. First one is where the first domain contacts each domain separately. For that, then authentication and authorization relations are required between all domains. And then if routing option 2 is the one I've just described is used, then each domain must signal back to the first domain what the next one's going to be. Then there's another option where domains only exchange signaling with their adjacent domain. If routing option 1 is used, then the signaling message must contain a complete list of domains. But there, the AA adjacencies are only required between adjacent domains. How does the route get calculated? Well, we figure that initially some static routing tables will be good enough, but essentially later on you might want to make it a bit more scalable, you might want to use a protocol to distribute that into domain routing information similar to BGP, or some people are saying, well, BGP is possibly the most appropriate way to go. But that's a little bit further down the line. So here are the diagrams to show that. Essentially, there's the inter-domain manager, domain manager, and technology proxy, and then below there's the cloud, that is the data plane, essentially, that is the network elements that are being managed. And here is the two options. So this is signaling option 1, where the first domain connects the domain manager in each of the subsequent domains. And as it says, as I've already mentioned, in the case of routing option 2, then domain 2 must signal back the next domain, which in this case is domain 3, and so on. The other option is that the routing message, that the signaling is going from inter-domain manager to inter-domain manager in successive domains. In this case, if routing option 1 is used, then the signaling message must contain a complete route list from the beginning. So what I wanted to show there really is that the guys working on the architecture have finally started to sit down and discuss the issues that essentially we're going to come across with trying to design this multi-domain bandwidth on demand service. So now is essentially the time to start liaising with other projects working in similar areas. And the first of those is essentially the service activity 3 in GN2 that I've already mentioned, and that itself has a very close relationship with part of the EGEE project that you'll hear about later during the course of this conference. And essentially, EGEE is the project in which a production quality grid is to be built across Europe. One of the activities in EGEE, JRA4. This, by the way, is where we have an immense amount of probability to confuse things, because both EGEE and GN2 are the same structure, so they both have JRAs and service activities and so on. But here I mean the EGEE service, Joint Research Activity number 4, which is about network services development. There is actually a talk on this, as you can see, on tomorrow at 4 o'clock. But the work that they're working on have two aspects. There's network performance measurement, but there's also a bandwidth allocation and reservation activity, BAR, which, as you will also notice, unfortunately has the same acronym as the joint research activity that I'm talking about now, this BOD development. That's being done by people from the University of Edinburgh, Peter Clark's group. Dante are also involved in that, Sierra and Esgar, and DFN and CCLRC, as you can see. And what they have done there is, apart from cultivating a close working relationship between network providers and the grid users, which is obvious, what they've done is they've drawn up a clear distinction of duties between what the grid middleware will do and what services will be provided by the network operator. In this case, that is going to be Géant or Géant2 and some of the NRENs, GAR, Giannet, possibly Ukerna, who are implementing a premium IP service with advanced reservation. So premium IP is a diff-serve-based service that was developed a few years ago as part of a European project called Sequin. And as part of that distinction of the interfaces, an interface has been defined, and it's illustrated in this diagram here. So this is the architecture of this bandwidth allocation and reservation coming from the grid community. And so, as you can see, this is the bar component from EG, from the grid. This component here, the network service access point, is essentially the component that the service activity 3 in Géant 2 will develop, and that is where the premium IP reservation will be done. So this interface has been defined in high level, and one of the components there will be the premium IP reservation system, and then here is the network, which is again at the moment IP based, over which the premium IP reservations will be made in multiple domains. So at the moment, what we're thinking of doing is combining our efforts for this more layer 1, layer 2 oriented bandwidth on demand and working out where it fits into this architecture. So there's essentially two possibilities. One is that we become a lot more fully integrated with this network service access point component concept. The other one is that the network service access point essentially becomes a client of whatever provisioning components we develop ourselves within our more bandwidth on demand oriented project. So the other thing that this diagram actually shows, again Bob touched upon it, is the debate that we had ourselves of whether or not our services should be edge to edge or end to end. Well, obviously they need to be end to end as much as possible, but the reality is that they won't be initially. The service will go as far as it can, as close to the user, and then it will have to stop. And the users will have to have some before this local network service access point gets put in place. Those users are going to have to set up manually set up, if you like, the equivalent of a local loop to actually get to the point where the service can actually become more dynamic. Okay, in the last minute or so, I just want to draw a few conclusions of where we are. The initial survey work has been completed, so clearly there was a latent demand for a bandwidth on demand service, but I can't say that I was overwhelmed by a big response. The grid and the big science users are clearly the most likely users. We need to revisit this survey that I talked about earlier on, and I think, as I said before, the only way to actually get to the foot of the real requirements is to actually talk to them, sit down in a room with them and talk technical details and do some serious whiteboarding. Creating questionnaires and distributing them is just simply not the way to do it. The service specification discussions are now ongoing, so I've tried to give you some insight into the discussions that are ongoing. A draft framework is being drawn up. Now we need to compare notes with those developing projects in similar areas. I've not mentioned the others. I mean, there's obviously we need to start comparing notes with our colleagues on the other side of the Atlantic. So as you've just heard there from Bob, and the Internet 2 work, the Dragon project, and there's other activities in Europe working in similar areas. So the Viola project, the Muckbed project. For now, what we're thinking, what we're going to do in JRA3 in our own activity is essentially start off by defining information flows and the functions of the blocks that deal with that information. And I've given you a bit of an insight into that architecture with those domain manager, inter-domain manager, and technology proxy. Once you've defined the information that's required to flow between the domains and from the users to the first domain, you can start to streamline the manual processes, and then the automation comes in bit by bit as you move forwards. So it's possible to build this inter-domain manager that can automatically handle call requests, but initially that inter-domain manager may just send a mail to the NOC in a particular domain saying, please set up this part of the path, can you do it? And if they say yes, they'll send back a message, and then the inter-domain handler will deal in an automatic way with the signaling across between the domains. We'll need to do some testing, obviously, at some point. As we get more automated, we will have to start using a test bed, because we can't do this testing on the production network. That's quite clear. And finally, we may be in a position to pilot a service towards the end of the Géant 2 program, and maybe it might be a production service for Géant 3. So at that point, so thank you for listening.
Questions? John, right there. It's working.
Is this? Yeah, it's working. I have a general question addressing both Bob and Michael. I'm interested in how the technology interfaces with the antisocial professor. So one of the problems I can foresee in these automated bandwidth reservation systems is that bandwidth is reserved by a particular individual or a particular group for some indeterminate period of time, possibly denying service to others. And are there proposals to police the reservations that are active at any particular moment in time, so that you can see whether people are making proper use of the bandwidth they've reserved, or considerations such as that outside of the scope of this work?
To some extent, we're looking at the technology for being able to actually make the service possible. I can see where you're coming from. I mean, one of the arguments you might say for policing that kind of use of the service is to actually charge for it, but that's not really possible. So I mean, the monitoring has been considered as being one of the ways in which you might actually make sure that the services are being used. I mean, initially monitoring was just thought of being a way of checking the quality of the actual links, but others have said, well, no, actually, you may want to check that they are being used. I don't know if Bob wants to make a response as well. He's not here, I don't think.
Exactly. Bob, do you want to add anything to that?
I mean, essentially, from our point of view, we are aware of policy issues like that, but that really, I mean, we can't cover all of those aspects, so that's really for future work, essentially.
Okay. Okay, let's thank Michael for his talk.
Clip is on.
Our next speaker is Gianna Ferrari, who is a PhD in electronics and communication engineering. She works on networks for the National Institute of Nuclear Physics in Italy, and she was going to talk to us about grid reservations for network access.
Okay, let's try. Okay, thanks. Can you hear me? Yeah. So yes, thanks for the introduction. I'm with the Italian National Institute for Nuclear Physics. I already know that with this presentation I'm going to kind of disappoint you because I'm not going to talk about how bandwidth is going to be provisioned, at least what is our approach. We have already a presentation about that which is scheduled tomorrow afternoon. This presentation is more about what are the bricks, the components that we currently miss from a middleware point of view in order to enable the grid system to perform reservation. Not only network reservation, but also other types of resources are considered. For example, storage is extremely important and computing. So what I'm talking about today is just what we are trying to push forward in order to enable the users, the grid users, and also the applications. So not only the human beings, but also the agents and the grid services. What are the bricks that can enable these components and allow them to perform a reservation in the system? Okay, thanks. So we start with a few use cases, and first an introduction on grid because it's a buzzword and sometimes it's misused, so I want to set the context first. I will also talk about the work that has been done and is still ongoing at the Global Grid Forum in terms of SLA signaling. And next I will show you what we plan to do in terms of SLA signaling in the grid, and especially the integration of this functionality with a very important key service in grid computing, which is called workload management system. I will also tell you what are the progresses in terms of implementation, and then show you the future roadmap. As I said at the very beginning, the most important point for us is to define some common and general services that we can use independently of the nature of the resource that we are handling. So we don't want to provide and implement services that can just be used for networking, but also for storage and computing reservation. We have a number of urgent use cases that we have to support in the grid. I started with the network just because this is a networking conference, not because the network is the most important resource for the grid community. And I know that this is a strong statement right now, but I think this is the reality. We have been focusing on the problem of quality of service, DIFSER technologies, ATM, MPLS for many years now. And we still don't see a mechanism that works in an inter-domain scenario. So I have to say that at the moment, the network is not a critical point for most of the grid applications. The most important scenarios are computing storage and computing reservation and storage reservation. Just to give you an example, it doesn't make any sense for a grid application to use millions of CPU cycles somewhere in the world to just execute a large number of jobs when you don't have storage to save the output of your analysis. So in order to really carry out this kind of workflow, you have first to store the needed space on a storage system, then store CPU cycle, reserve CPU cycles, somewhere else, and then start the workflow. The network is, of course, important. I'm not saying that networking and bandwidth reservation is not important, but today we all know that it's kind of very complex task to carry out in a true wide geographical scenario. So we are still trying to focus on that, but basically on the high-level services that should enable all this. From a networking point of view, we have two important use cases which were worked out by our colleagues from the JRA4 work group from the EG project, which are bulk transfer and virtual disk line. Bulk transfer means that you typically want to start a high priority executable on a given farm somewhere in the grid only after having transferred the input files. You don't want to have a very large number of idle jobs waiting in a farm and using, well, just consuming CPU cycles waiting for the input files to be transferred around the world. So the typical thing you want to do is to first you reserve the bandwidth, then you transfer the data, you reserve CPU cycles, you start the executables, and you continue the workflow. The second use case is virtual disk line, which means typically for applications such as the ones that were presented today during the plenary session, you typically need a real-time requirement support in the network. So this would be rather the allocation of continuous bandwidth between two endpoints in the system. So what is the Global Grid Forum doing in terms of SLA signaling? We have this initiative, well, it's a working group actually, which is called the Grid Resource Allocation and Agreement Protocol Working Group, that is trying to define the architecture and the standard, which is based on web services technology, to implement a two-layer architecture that is shown in this picture. At the top, we have the so-called agreement layer level, which is the signaling layer, which provides the facilities to a user or application to exchange information about the SLAs that are requested. And at the bottom, the service layer, which is, from a networking point of view, the network with all the technical mechanisms to enforce the reservation. So typically, users and applications do not talk at this level directly, but rather send requests to an intermediate brick, which we call agreement service. This is a service that we are trying to implement in the framework of the EG project. So GLITE is an acronym that stands for, is basically the acronym that summarizes the entire system of services that the EG project is trying to developing. Not only the agreement service that I mentioned before, but everything from security, accounting, monitoring, workload management, information services, and etc. All the important mechanisms that a grid needs in order to work. So the specification which is under development at the GGF is called the WS agreement. Is basically proposal, as I said, based on web services technology that aims at standardizing the structure of the service level agreement in terms of an XML schema definition. It also defines the standard interface of the agreement service that is responsible of handling the exchange of SLAs between a user and the service layer. So the agreement layer, again, is something in between, the glue. And is also responsible of checking compliance of the agreement to internal templates that have, of course, to be defined prior to signaling in agreement with the service providers the agreement talks to. And is also responsible of finding the appropriate service provider that should be, in principle, be able to honor the guarantees that are requested by the user. So we tried to, I forgot this slide. This is important. It's just a picture to show you what is the XML structure, which is much more complicated if you see that in XML. So we have a general agreement element which contains the name of the agreement, some context information which tells what are the partners involved in the agreement signaling process. Then we have the terms, which are the attributes that characterize the the contract and the service that is requested by the user or application, and the guarantee terms that are actually the attributes that specify what is guaranteed by contract, and also the penalties in case either the user or the service provider do not honor the guarantees that were specified in the SLA. So in the EG project, we basically stick and try to comply to this GGF standard, but currently we are kind of deviating from that because there are some technicalities that we are not supporting right now. But from a high-level point of view, we are completely compliant. The agreement initiator is the terminology that we use to identify the users or applications or agents that are responsible of starting the signaling process. The agreement service, again, is this intermediate component that is needed in order to mainly perform monitoring of the signaling process and the compliance checks. And then we have the resource reservation service provider at the bottom, which could be a storage element, which provides just a space for data, computing farms, and the network. This is the architecture we are trying to develop. So at the bottom, at the top, we have all the types of users that we are trying to focus on. The most common scenario is the human being that is able to generate this SLA request, for example, with a web interface, which was similar to what was presented at the very beginning this afternoon. The other initiator is the data scheduler, which is the grid component that is responsible of triggering data transfers between endpoints in the grid. The other important use case we have in mind is the workload management system, which is the component that receives from the user requests, for example, job submission requests, and is responsible of doing first discovery of all the computing elements, the computing resources that can accept the job, and also is responsible of doing logging and bookkeeping of the entire process, and also responsible of managing the input-output transmission of the files that are generated and used by the executables. For us, the WMS is a potential user because when we have a general purpose human being, typically, especially in case of computing and storage, you don't know in advance what are the endpoints involved in the reservation. So the WMS has already the machinery to implement the discovery process. It relies on the grid information systems in the network, in the grid infrastructure, and mainly on an internal repository of information that is used just to speed up the process and decouple the efficiency of the service from the efficiency of the information system. So we thought this is a very important component, especially for storage. You typically don't care where you store the data. You're rather interested in where, how you want to access the storage system, with what protocol, and how much data you want to reserve. Where actually that data is going to be placed is not relevant to the user, typically. And that's the same for the computing element. In the grid, the basic assumption is that you do sharing of resources. So you don't typically ask, I wanted to run my executable somewhere, but you just say, I have this executable with these requirements. Please find the best computing farm that can handle my requirements. We also use discovery for networking, because in general, in a general scenario, we may have different paths, not only a single path that can provide connectivity between two endpoints, and in general, you may also have different enabling technologies. So in principle, the user may be willing to specify what is the best path and what is the best technology that he is willing to use. This is just a more specific picture which shows that in general the agreement initiator, for example the workload manager, is able and should be able to talk to different agreement services. So the input parameters here are the offer, in other words the service level that has agreement that has to be contracted and signaled. And we may have different instances of agreement services around the world. We just don't have a single bottleneck, but this service is replicated. And we have a different resource instances at the bottom of the stack. So the service provider is, for example, in case of computing, is responsible of accepting the request, checking the local database, see if the resource is available during the time frame specified by the user, if there's any. And is also responsible of doing authentication and authorization. There was a question, I think, at the very beginning after the first presentation, asking how do you want to handle authorization and authentication. This is absolutely terribly important because you cannot do any reservation of anything if you don't first authorize and authenticate who is talking to you. And in order to comply with the typical approach used in the grid, especially in the EGE project, we handle X509 certificates for that. We already have policy databases that provide information about who is allowed to do what. We have what we call virtual organization membership services that for a given user tell what are the roles of the user for a given community, what are the responsibilities, what are the rights, and according to that, that information is carried in the certificate of the user along with the request, and all the services involved in the signaling process can analyze that, check the rights according to the membership, and then add on top of that the local authorization, which means that after you have authenticated and after you have decided what is the virtual organization involved in that, you can decide if the user or agent or grid service is authorized to use the service that was requested. I think that I have already more or less presented what I'm going to show in this slide. So I will present the details of the three most important components in the architecture that I showed previously. So we had the service provider at the bottom is responsible of checking the availability of the resource, of doing authorization and authentication. And this is the place where we see the network. From our perspective, the network is a kind of black box. And in fact, this is basically the same picture that was showed before by Michael. This is the network. We have different domains. The network element, which is also called the bar now, is the entry point for the grid software. Here we have the agreement service that I introduced before and all the other grid services that may request for bandwidth. So the agreement service is something that sits on top of the network element and is typically the proxy for any grid user and grid agent. The agreement service is the novel component that we are trying to implement right now and is again modeled according to the GGF approach. It can talk to any service provider in principle, but of course you can understand, especially when the resource interface is not standardized, the agreement service will be capable of talking the language of the service provider only if it was implemented to do so. So in general, we cannot think about the agreement service as a standalone service that can talk to anybody, to any computing farm, to any storage element, to any network provider. It has to be specialized. Unfortunately, for the networking reality, we don't have a kind of standard interface right now. But for example, in case of storage resources, there's already some effort ongoing in the Greek community trying to standardize the language that you need in order to reserve a space. So in that case, it's kind of simpler. But for the network, that's not the case. So we just assume that in the system, we may have different agreement services with different capabilities. So now the problem is, if you are a user or a workload manager or a data scheduler, how can you understand or how can you decide what is the best agreement for you that is actually capable of talking the language of the resource where you in the end have to resource and set aside to reserve and set aside the resource? That's done again through the discovery machinery that is already available in the workload management system of the grid. We have a discovery process that starts from the bottom. First, you have the user that asks for a given resource and specifies the requirements. The requirements are extracted by the workload manager. Then there's a matchmaking phase that takes the requirements, checks all the resource instances available in the system, compares the capabilities, and selects only the instances that are able to satisfy the requirements. When you know the instances, you need a schema, a high-level projection of the capability of the resource, telling what are the functionalities. For example, I can provide you bandwidth guaranteed, but between a minimum or a maximum. I can provide you guaranteed packet loss or something like that. So that has to be coded and specified in a high-level projection of the resource. When you have that, you can decide what are the resources that satisfy the requirements and provide the service that you requested. But that's, again, not sufficient, because you now know the resources, but you have to determine the agreement service that can talk to that resources. So we need an additional piece of information in the schema of the resource that tells you what is the interface. After that, we have again another discovery cycles that goes through the list of the agreement services available that you are authorized to talk to, and only selects the ones that support the interface of that specific resource. After that, basically the discovery process is finished. You know all the resources that you may want to reserve and are capable to supply the requested resource and satisfy the requirements, and you already know for each resource what are the agreements that can talk to that box. So the agreement initiator is at the top of the stack, as I said at the very beginning, and is the user. Why did we decide that having this component talking to the WMS, the workload management system, is a good idea? As I already hinted before, we think that in general this is a good solution because the WMS already have these discovery capabilities. But this is not the only reason. The WMS is already instrumented with logging and bookkeeping facilities, which means that the entire signaling process from the submission of the request, that is in our case the submission of a SLA, to the end of the process, which is the enforcement of the guarantees that are requested, the entire process is logged, and you have a place where you can understand what is the current status every time, for example, you lose connectivity to the WMS or to the resource or to other grid services that are involved in the grid signaling process. So this is just fundamental services that typically we neglect when we think about just reservation, but which are necessary in order to have a robust mechanism working in reality. And there's another important, not minor, but very useful functionality available from the WMS, which is a resubmission, which means that, for example, you try to reserve bandwidth in a given interval, but no resources are available at that time, or, for example, you have no service provider that is answering to your question in a given interval, then you can keep the request in an internal queue and try to resubmit that request in the future with an internal policy, which is, again, another layer for robustness. I think I will go very quickly through these slides. This is the WMS, the workload management system we have today for a job submission. We are trying to instrument that box with additional components that we need in order to support SLA signaling. And these components are basically a reservation manager that is responsible of handling co-allocation and handling also the discovery process to decide what are the external agreement services that he has to talk to. And of course, we have to add components in order to talk to the logging and bookkeeping component of the WMS. This is the discovery that I have already presented before. So I think that I'm also now at the end of the presentation. I can just give you an idea of where we are right now with the implementation work. We started with storage because it's kind of simpler resource, and as again said at the very beginning, it's something that is mandatory for any grid application. So we are trying to instrument the grid services in order to support storage reservation. This means that we have now an available a reservation manager that is able to talk to a space reservation agreement service. So this is already implemented. And this guy talks to mass storage systems that expose an SRM 2.1 interface. SRM is this kind of a standard language that is spoken by storage devices. SRM is an acronym that stands for, I think it's a storage resource management, and it's a very general purpose interface that allows you to put files, get files, remove, abort transmissions, and do reservation of space as well. The methods that are exposed by these reservation agreement services are general, and they are listed on the slide. They are create agreement. It's a method that you invoke in order to request the start of the signaling process. Get templates. It's the operation you invoke when you want to know what are the agreements that can be understood by the agreement service. So you retrieve them. They are XML files with a standard structure. And that's the structure that you have to comply with when you want to submit your SLA request. You have the get agreement property operation that is used when you have already started the signaling process and you want to know if the agreement was established successfully and what were the attributes of that agreement that were actually guaranteed by the service provider. Agreement kill is to just abort an existing agreement, and the get agreement status is for monitoring. Just a few pieces of information about the technology that we use in order to implement the service. We use the web services technology, which means that we use the SOAP protocol. It's an XML messaging protocol that tells you what is the standard structure of any message exchange between the two entities. SOAP is based on XML and typically relies on a binding protocol such as HTML, which is one of the most common ones used. We use the XML schema definitions from the GGF, so the template that is exchanged between the initiator and the agreement service is standard. We use the GSOAP 2.7 because we are developing in C++. And again, the service that we have been interfacing with to test the agreement service is called Storm. It's a storage element supporting space reservation with an SRM 2.1 interface. This is a simple example of what an agreement offer. In other words, the service level agreement looks like in XML. It's just the details. It's for your own reference. You are curious. It's just a structured way to represent the agreement in a standard way, according to the GGF. So this is this last slide. It's future work. Of course, we have a prototype right now, but we want to extend that one with more authorization and authentication capabilities. We didn't focus on the problem of co-allocation. For example, when you have a workflow and you want to allocate space, computing, and, for example, bandwidth to transfer the files from a storage element to your computing farm. So that's still to be done. It has to be still integrated with the logging and bookkeeping component of the WMS shown before. And of course, we still have to understand what is going to be the interface that has to be spoken and used by the agreement service when we want to reserve a bandwidth in the network. So that's basically something going on in collaboration with the JRA for colleagues from the EG project. Okay, so I think this is all. I don't know if you have questions.
So the buses will leave in 10 minutes, so let's take one or two quick questions. Any questions?
Okay.
While you're thinking, I'll remind you you should have received email by now with a link to the online feedback form. So it was easy today because you had 3 excellent speakers this afternoon. But do go to that form and fill out your feedback. Any questions?
Is it a kind of exam?
All right, well, thank you very much.